Hi once again. So we will discuss the continuation of the symmetrical component analysis, and just a recap of what we have discussed on the last slide. We discussed positive sequence and negative sequence. Okay, today we will discuss zero sequence components. So the definition of zero sequence components is they are a group of vectors which has the same magnitude and the same direction. So it simply means that any vectors in space, okay, IAO, IBO, and ICO, or the zero sequence components of the line currents is the same. So we can have that at equation number 1. Okay, so zero sequence components are equal to each other. There's a phase A, phase B, or phase C. Also, we can recall what we have discussed from the last slide, that we can get the positive sequence components in terms of its corresponding reference. So our reference here is your line A, okay, current, or line A current IA. Now we already have the relationship of IB1 to IA1 and IC1 and IA1 in terms of operator A. So we have A squared IA1 and AIA1 respectively for IB1 and IC1. Now how about the negative sequence components? So the negative sequence components in terms of IA2, which is our reference again, is line A. So they are the inverse of the positive sequence components. So if this is A squared, then in terms of IB2 and IA2, this is in terms of A. While IC2, okay, in terms of positive component, that is AIA1, but here it is A squared IA2. Please take note that A is 1 bar 120 and A squared is 1 bar 240. Okay, and it's basically comes from an identity of the vector property. If you have an x bar theta, if you raise it to an n, and then it will yield to this identity or property. Okay, so it is already automatic that if you want to have a to the cube, since this is 1 raised to the cube is 1 bar 360, and then a to the fourth 1 bar 480, so far and so forth. So we already discussed this one from the last slide, but we just recall why it is like this, simply because of this property or identity, that x bar theta raised to the n is equal to x to the raised to the n, and then that angle theta must multiply by it by n. Okay, let's go back to Fortescue's symmetrical components definition, that any unbalanced system of voltage or currents in terms of line or phase is simply equal to the positive component, negative component, and the zero component. So I have this format. Okay, it's not it's also in B. It is the same thing. Rather, you have the zero component B, the positive component to B, and the negative component to B. It is also the same thing with IC. You have the zero component, the positive component, and the negative component respectively. Now I have that equation number 4. If we substitute 1, 2, and 3 to 4 corresponds to, again, our reference is line A. So it means that you must solve this equation in terms of the components of A, because A is our reference. And if you do that, the answers or this corresponding equation yields this important matrix, which we will do here, that IA is simply equal to IAO, IA1 and IA2, in terms of IB, which is with reference to IA, IA0 plus AIA1 plus AI2. As you can see here, this IB here is this IB here. So it becomes A squared IA1. This IB2 here is also this IB2 here. So it becomes AIA2. So as you can see, it must be in terms of line A reference. And if you do it on C, it will be the inverse of IB. So AIA2 and then A squared IA2. Okay, now before we okay, I need the eraser. Before we conclude this slide, we must have, okay, thank you, eraser. Okay, my eraser is on the topmost part. Okay, so we need to have a matrix in terms of matrix. So in terms of matrix, we can have this scenario: 1, 1, 1, 1, 1. Then you have A squared, you have A, and A squared. And then you have your IA0, IA1, IA2, and then you have your IA, IB, and IC. Please take note, all of these are vectors. Even the components are vectors, by the way. We can have this matrix, an equivalent of this equation. So this is equation number 5. And this will be our equation number 6 in terms of matrix. So using matrix or matrices, if you have this column here and then you multiply it by this row, you will have that this cumulative sum or this sum. So this is IA, IA1, and IA2. And then you have your row here, and then you have your column here, and your row here. So you have IAO, A squared, IA1, IA2. And then you have your column here, another row here. You have IAO plus AIA1 plus A squared IA2, which is equivalent to this. And please take note, the most important part here is this. I called an A matrix, which is we will do, or we will have that equation on the next slide, which is very important. Okay, let us conclude our discussion here and see you on the next slide. Hello once again. So we will continue our discussion on symmetrical components and the conclusion of this topic in terms of the overall concepts. Okay, let us recall the last equation that we have done on the second slide, which is equation number 6. And this equation number 6 is the so-called Fortescue matrix number 1. Okay, simply because this Fortescue matrix number 1 is, if you can see on the equation, your required is your line currents, and the given on the right side of the equal sign is your components. Okay, so Fortescue matrix number 1 is the required is your line currents or line voltages, phase currents or phase voltage, and the given is the components of the line current IA. Now how about if that is the other way around? You want to compute for the components. Okay, you want to compute for the components given the line currents or line voltages. Okay, what you will do here is just a little bit of matrix manipulation or matrix algebra. This is the column vector. I could say I, A, B, and C. And this is what we have done last slide here, that we have this as an A matrix. So please take note of that. And you have here the components 0, 1, and 2. IA 0, 1, and 2. Okay, for that, we need to get the column vector of the components. So in order to do that, we will make use of matrix or matrices. So instead, we use here, you cannot divide a matrix first, but instead that is in terms of inverse. So you need to inverse this matrix here, which is your A matrix. Not 1, 1, 1, 1, A squared A. Then 1A and A squared, you need to do the inverse of that matrix. And then IA 0, 1, 2 is already on the left side of the equation, which means that this is our required and the right side is our given. So that is other way around, which is what I meant here on Fortescue matrix number 1. Now our requirement is the components and the given is line voltage, line current, phase voltage, or phase currents. Okay, without further ado, the inverse of this matrix, so A matrix, is this matrix here, which is 1/3 of this, okay, matrix, which is 1, 1, 1, 1, A, and A squared, 1, A squared, and A. And then I already have this as a column vector, and then this and another column vector here. So the answer is simply this equation number 7, and this equation number 7 is the so-called Fortescue's matrix number 2. Okay? So you can solve already here IA0, IA1, and IA2. Okay? But how you will solve IBO, IB1, IB2, ICO, IC1, and IC2 respectively? So you need to recall equations 1, 2, and 3 from the previous slide. So we can do this here a little in this slide. For example, our given, sorry for that. So I will make use of this red pen instead. Okay, our given is IA, IB, and IC. I want to get IC1, for example. So go to this Fortescue's matrix number 2 because our given is line voltage, line current, phase voltage, phase current, and we need to compute for the component. So get IA1 first because we know IC1 can be solved if you have your respective reference, which is IA1. Okay, for this, we can use the column row technique here. This is the column, and then you see here IA1, okay, and then this is the row here. So using matrix. So you have here IA1 simply equal to 1/3, okay, of IA plus IB plus IC. Okay, but you have here, you have your A, IB, okay, and you have here A squared IC. Okay, so you already have the equation for IA1. Now, how can you get IA1 in terms of IC1? You can recall one of those equations, okay, which is equation number 2, if I'm not mistaken, on slide number 2. So, you have IC1 equal to, now if you forgot what is the A and A squared, and you see here positive component, which is 1, just recall that is an ABC sequence. So, you have an IA1, this is from the derivation from the first slide, IB1 and IC1, you can see it is positive 120 degree based on the reference IA1. So that is IA1. Okay, pretty simple, right? So all you have to do is to go back to what we have already started, which is the basic fundamental. And if you know all of the fundamentals, you can solve any problem on symmetrical components, especially you're considering unbalanced condition. By the way, before we end this one, okay, and before we go to the problems, please take note, okay, that we have here the two important equations, Fortescue's matrix number 1 and Fortescue's matrix number 2. They can be applied in voltage as well. Okay, all you have to do is to change all of the i's to V. You have VA, VB, and BC, and then that will happen. What will happen here? VAO, VA1, and VA2 respectively. So just change all of the i's for B, okay, and then you are good to go because those VA, VB, and BC and IA, IB, and IC dependent if that is phase or line. Okay, so let us go to problem solving for the applications of all of these equations. See you and maraming salamat.